Ciao, buongiorno. Hello, hello everyone. Welcome back, and I hope you can hear me well.
Yes.
Yes.
Yeah, thank you very much. Thank you. Good morning. I start the recording now, and the YouTube streaming has been activated, so you can either attend the class here on Teams or on YouTube. All right. Okay, so welcome back everyone. I think we can start with lesson number 3. Let me share my screen. Okay. And here it is. The idea, the plan for today is to start talking about the modeling of fuel cells. In lessons number 1 and 2, we introduced a little bit fuel cells with the idea that at least some of you had no clue at all of what was a fuel cell, what is a fuel cell, what are the physical and chemical processes developing inside a fuel cell. Now that we have at least I hope a general idea of what are fuel cells and of the losses, we can start properly talking about CFD, which in a way is the core of this short course. So this is a picture that I'd like to bring up to your attention anytime we start, and you will see also when we will finish talking about the modeling using CFD of fuel cell systems. And I think that this picture resumes what is really the key element of an accurate simulation of fuel cells. Or if you want to see in another way, what's so special about the CFD of fuel cells? I mean, we know that there are fluids moving around. Isn't it just like any other CFD problem? Well, in a way, clearly, yes. I mean, you have fluids, you can apply CFD. But there are some specific aspects that you have to keep in mind in order to provide an accurate simulation. And in our view, the key element, really the most important one, is the tight and accurate integration between these three simulation realms. On one side, you have multiphase fluid here. So you have fluids, and if you're talking about low temperature fuel cells, this is multiphase, because you might have locally saturated conditions, so your water vapor might condense and become a liquid one. So it will always be in this type of fuel cells a multiphase fluid modeling. So we already introduced a particular aspect of CFD simulation. Then we have solid parts. So it will be not only more than one phase, but also more than one physics. Well, which are these solid parts? Clearly, the membrane. It's a solid polymer, and it will always be present in a simulation of a fuel cell. Then we have the bipolar plates. These are conductive parts whose I mean, multiple roles. We will talk about this is structural role, heat dissipation, charge conduction. So yes, we have another solid part. And then we have a lot of porous materials, gas diffusion layers, catalyst layers. So these are composed by a solid phase which leaves some voids for the fluid, but indeed we have some solid phase, these fibers, these solid fibers. So it will always be more than one phase, but also more than one physics. And so the solid physics needs to interact with the fluid one in order to have an accurate simulation. And then we have a third simulation framework, which is the one related to electrochemistry, clearly. And electrochemistry interacts both with the fluid aspects, and we will see today, I mean, electrochemical reactions consume reactants and produce products. So these reactions have to be coupled with the fluid modeling, but these reactions produce also currents that will travel along the solid components, the ionic current through the membrane and the electronic current through the conductive parts. So this is why we have, for all of these three simulation framework, a two-way interaction. All of these have to be coupled with the other two. And as a background to this triple interaction, we have I really emphasize paramount importance of the material characterization. In the context of fuel cells, an accurate characterization of materials is of utmost importance, because the impact that this has on the accuracy of the results, whatever results you might looking at, current density, thermal distribution, whatever, it's incredibly linked to the accuracy in modeling your materials. And this, especially for CFD modelers, is also a cause for uncertainty, in the sense that most of the times we will not have a perfectly accurate characterization of our materials. As CFD modelers, I mean, we have to live with that. We have to accept that some materials will not be perfectly characterized as we would desire. So it's our goal also to have a sort of sensitivity of the material property on the result. So we have to keep this in mind, okay? But I think that this picture, we will see how this can be integrated during this lesson, is really resuming all the fundamental aspects of the CFD modeling of fuel cells systems, okay? Now, our obvious, if you want, starting point are the general conservation equation or transport equations typical of any CFD problem. So I assume that most of you have at least a basic knowledge of these conservation equations. Basically, they resume, they replicate on a mathematical form the fundamental physical principles of the conservation of mass, the so-called continuity equation, conservation of the momentum, and this is a vectorial equation, in the sense that you can get from this three scalar transport equation, one for each direction in space. You have the generic conservation of the mass fraction of a generic species. Mass fraction is usually indicated with this Y letter of the kth species. You have the conservation of energy here. And this is a set of coupled and partially differential equations that describe in any computational fluid dynamic problem, I mean in any fluid dynamic problem apart from the computational side, the basic conservation principles of physics. When you apply CFD, so when you want to solve these equations using a solver, a computer, you have to discretize this, and then you get to the CFD technique that we are used to. So in a way, these are our tools for CFD. It's like the fork and knife when you eat, when you want to apply CFD to solve a fluid dynamic problem, you use this kind of transport equations. And generally speaking, they all follow a common model. And the model is the generic transport equation. So you see that, for instance, if we look at equation 2, 3, and 4, we find some similarities. We have an unsteady term. This represents the variation of that specific transported property with the time. Then we have a term related to the advection of that property, so the transport of that property because of the mean fluid motion. And then we have some diffusive terms, like this one here and this one here. So diffusion is another process of transport, a transport not related to the fluid motion, but a transport related and driven by a gradient in concentration. So we might also have a transport even if we have a perfectly quiescent flow field, just because we have a gradient of some quantity, like heat or a concentration of a given species. So advection and diffusion are two different transport mechanisms. They can coexist, and this is what these equations are representing. Then we have also some other source terms, like pressure gradient here. Pressure gradient creates a motion. Or this S something terms here. These are the source terms, and I will always talk about source in an algebraic sense. It might be positive if that variable is created, or negative if it is consumed. And they all will be specified based on the specific equation that we are using. Okay? Just, been walking around Hogwarts. Just a second, sorry.
काचा बंद करून ठेवतो.
I have to here. All right. I can share again. Okay, so this in a nutshell is how do we use the generic model of a transport equation that you see here. It can be declined basically for any variable of interest for our CFD problem. And this type of model, the transport equation model, has been used and has been adapted to also completely different CFD problems, like, for instance, combustion modeling. For those of you who are familiar with combustion modeling, there is a wide use of the transport equation model adapted to variables specific to the combustion context, like flame surface density or similar other variables. Okay, so this was to resume a little bit the context that we are in, and the equation, the four equations that you see here, basically can be applied to any CFD problem. Now, and also to the fuel cells problem. Now we will see how this can be specified for the solution of fuel cells using CFD. Okay. And just to conclude this, if you'd like, or if you need some basic concepts about this equation, sources 1 and 2 are two excellent textbooks for rudiments of CFD. These are the Verstegen Malala Sekira book and the Ferzinger-Perich book. Okay. Now, the equations that you've seen before describe the generic fluid motion in any regime. There is no distinction between laminar and turbulent in this equation. Let me just step back one slide here. If you have a turbulent problem, then you will have to specify, to introduce some turbulence models. But strictly speaking, these transport equations are universal, so they can be applied to any kind of flow, any kind of fluid motion. Now, in the context of fuel cells, we might introduce some very useful and very convenient assumptions. The first one is this one. We can always refer to laminar flows. And how can we be sure about this? clearly, a check based on the fluid velocities would always have to be carried out. But generally speaking, the velocities that we have in fuel cell systems regarding the fluids are extremely low. And they are extremely low in the gas channels. And once the flows develop inside the porous materials, these velocities become even smaller. So generally, we are in the range of a few hundreds of Reynolds number, which typically well justifies the assumption of a laminar flow. So we can expect, with a good approximation, extremely slow flows, and this justifies the use of laminar flow models. So apart from very specific cases, I would say that 99% of the fuel cells models assume laminar flows. So as CFD modelers, we don't have to care about turbulence, which I mean is a great simplification of our set of equations. Okay, so we can work with laminar flows. The second assumption that we can introduce is this one: steady state flows. I mean, as you know, in nature, there is no such thing as a perfectly steady state flow. And the flows and turbulence are by nature time dependent. But what we are saying here is that from the point of view of operating condition of fuel cells, we have time scales in the order of minutes, or at least tenths of seconds. So if our goal is to describe the behavior of a fuel cell and of the fluid dynamics in within, we can introduce the assumption of steady state flows. Just as a note, this doesn't mean that we are not interested into the dynamic behavior of fuel cells. I mean, we will not say it in this course, but for your knowledge, there is a lot of interest into the, I mean, there is the perfectly equivalent of a driving cycle for an engine. There is also a load cycle. There are also load cycles for fuel cells. And a typical problem of high interest, especially for the automotive sector, is the cold start of fuel cells, because these proton exchange membrane fuel cells, because of their water content, which that, as we said, is so crucial for their optimal operation, might encounter freezing issues, especially for long stop periods in winter conditions. Okay, so the cold start or the de-icing of this fuel cell is clearly a time-dependent problem of very high interest, and there are dedicated models for that. We will not see this, so the generic framework that we will consider is steady state. And apart from these specific issues that we've talked about now, I have to say that the majority of three-dimensional CFD models use these steady state equations. So the scope of this lesson is, by all means, to introduce you to the most common and widespread treatment, numerical treatment of fuel cells using CFD. Okay. Then, number 3, multiphysics. We already talked about this. We will never have a single component in a fuel cells. I mean, apart from basic flows or basic aerodynamic and pressure losses simulations of fuel cells, we always have to talk about more than one physics. We have, let's say, proper fluid regions, the gas channels, where we have just the fluid. Then we have the porous materials that will require a dedicated treatment. We have the solid parts, the membrane, where we have ion conduction, and the bipolar plate, where we have just electron conductions. So it will always be a multi-physics problem. And this will involve basically all the transport phenomena. I mean, if you are familiar with heat transfer problems, basically all fuel cells models are conjugate heat transfer models, because we will have the heat transfer between a fluid domain and a solid domain. And these have to be tightly coupled one to the other. So we will have a two-way coupling. This relates heat transfer, but we will see we will relate also charge transport. Okay. Multiphase, again, we already introduced this. Especially for low temperature fuel cells, we will always have to consider the presence of some liquid. As you might know, we will talk about this at the end. Multiphase modeling is a extremely wide range of applications using CFD, because you might have multi-phase issues in so many different industrial processes, in the food and beverage industry, in the oil and gas industry. Every time you need to predict in a way the separation of more than one phase, you will require a multi-phase approach. And there are several multi-phase approaches. We will talk about this. But bear in mind that for low temperature fuel cells, you might have gas and liquid. So this already makes more than one phase. But even if you are, let's say, that you operate a high temperature type of fuel cell, so you can, with good reasons, forget about the liquid. If you're running more than 100 or 120 Celsius degrees, you will never have a liquid. So you might think to work just with a single phase. This is not completely true, because apart from water in vapor and in liquid phase, you always have the water contained in the membrane, which you might consider as a third phase. Most of the times, this is called a dissolved phase to distinguish it from the other two. So even in high temperature fuel cells, you can't just deal with water vapor. There's also something else. Finally, macrohomogeneous. Macrohomogeneous is a way to model, to represent porous materials, which is extremely convenient from a computational point of view, and most of the times also necessary. What does this mean? It means, I mean, you might think as a porous material as maybe as a foam, okay? So a material where you have some solid leaving some space, some volume for the fluid flowing in within. So foams are porous materials. In our case, gas diffusion layers and catalyst layers will be composed by papers, literally papers of carbon pressed one above each other. So we will have basically solid fibers, a matrix of solid fibers, which are assembled one on the top of the other. Now, of course, we might think, I mean, what is the best modeling that we can do? We could reproduce the exact structure of the porous materials. This can be valid for foams, or we can do this for this particular type of porous materials. The problem with this is that if we want to reproduce the exact structure, and I mean by this the exact fiber displacement, fiber diameter, and irregularity in the fibers diameters and displacement, we will require at first extremely accurate characterization of our material that I anticipate you we will never have. So even if we could do it, we will not have the raw data that we will need. And secondly, this would introduce clearly an incredible computational overload. So just imagine that if you wanted to mesh the exact porous structure of a given material. So it is possible, there are models for that, but those type of models is related to the specific material characterizations. So just for you to know, there are CFD studies that are devoted to the characterization of porous materials. And in those kind of models, yes, you can, I mean, you have to, if that is your focus, replicate the exact structure of that material. In this type of models that we are considering here, we can't do this. I mean, the computational load will be just excessive, and what we can live with happily are just statistical, averaged properties of our porous material. So whenever we will talk about porous materials, we will talk about an average porosity, which is the volume fraction of the void, so the fluid, over the total volume. We will talk about the permeability of a porous material. okay, the tortuosity of a porous material, or effective conductivities, both thermal and electrical. So you see, in all of these properties related to the porous material, we will assume a concept of statistical significance, okay? Clearly, this might be an approximation, and as I was said at the beginning, this is where we are really at the edge of being accurate or inaccurate with our material modeling. But this resumes the macrohomogeneous type of model. So macrohomogeneous means statistical, a property representing the entire volume of my porous material. Okay. And just to conclude on this, always bear in mind that porous materials samples are never identical one to the other. Okay. So again, even if we wanted to introduce in our model the exact structure of my porous material, how can you deal with the fact that one GDL is different than another one? Which one are you modeling? So it's a little bit like turbulence modeling. You don't need, in most of the industrial problems, the characterization of each and every turbulent vortex. You might live well with some average representative properties. And in a way, this is the same idea applied to porous materials. Okay.
I have a short question regarding this.
Yeah, sure.
So I recently worked upon a structure for making the electrodes for both for a fuel cell and for hydrogen evolution reactions.
Mm-hmm.
So in that case, what we had was we had three-dimensional undulated structures. So I just wanted to know whether we can have a CFD model based on that. As you said, the material was graphene, thus it was highly porous. But even the macro structure of that of the electrode was not very homogeneous. So can we actually remake that?
Yeah, sure,
in this
sure.
case?
And the question of your colleague, I'm repeating for the students attending here in presence, is if we can apply this type of macro homogeneous models also to the electrodes. So the electrodes, I mean the catalyst layers, for instance, which are highly porous in nature, but where the electrochemical reaction really are developing. And we will. The answer is, generally speaking, yes. Also, the modeling of electrodes can be highly based on this macro homogeneous assumption. For catalyst layers, clearly this might be very critical. It might be very critical because basically we want to resume the electrochemical reaction rate, which is very local in nature, because reactions develop at the sites, really just at the sites where the platinum molecule or the platinum agglomerate is deposited, with some sort of volume averaged electrochemical reaction rate. So this might be critical, and this is why in the modeling of catalyst layers, we will talk about it next week, there is a class of models which is called agglomerate models. You might be familiar with those, that is trying to let's say, to put itself in between a purely macro homogeneous modeling and a locally based modeling of electrochemical reactions. Basically, just to conclude on this, you can't imagine to introduce in your model each and every site of platinum molecule for electrochemical reaction. Okay, so you can't imagine to do that. But you know that the platinum, if you look with a microscope on the electrode, is not uniformly distributed on your catalyst layer, but it forms these sorts of agglomerates. So a isolated cluster of molecules. So this type of agglomerate models devoted to catalyst layers have been developed to, in a way, go a little bit beyond this macro homogeneous approach. But so yes, to answer to your question, we can use this macro homogeneous approach also for electrodes.
Okay, thank you.
Yeah. Now, what we are going to introduce now is a generic framework of transport equation and all the details contained, diffusion coefficients, source terms, which is the most widespread modeling of fuel cells. Clearly, I say this because you might find in literature also other types of model. There is a wide variety of empirical zero-dimensional models. So if your scope is just to reproduce the polarization curve of a given fuel cell, provided that you have some empirical coefficients, you can reproduce the voltage and current curve. Okay, so just for you to know, those kind of zero-dimensional models, they do exist. But clearly, since they are not modeling the processes that are at the root cause of the generation of current, they only reproduce the trade-off between voltage and current. So you need to have some empirical coefficients. These are very clearly simple to be implemented. We are not talking about those, but they do exist, and there is a wide use of those in the industry because of their simplicity. Okay, what we are seeing here is a generic framework of equations allowing to reproduce and simulate all the physical and chemical processes developing inside a fuel cell. And the large-scale result of this is the generation of that current for a given voltage. But with this equation that we are seeing here, you can also investigate the root causes for that. Why do we have that current, and why don't we have twice that current? Okay. So this set of equations that we will see is, you might think at it as reported here, a unique set of equations for all the regions. This is a type of modeling framework that has been shared by really a lot of research groups, and it is extremely convenient. So the equations that we have seen before and that we will specify now will be shared by all the domains. So we will have a energy transport equation that will be applied to the fluid domain, the porous parts, the solid part, bipolar plate, the solid part, membrane, to all of this. Then, based on each material, on each physics, we will have a specification in terms of diffusion coefficients or source term. But this unified set of transport equations allows also a natural continuity at the region interface. Given that we have multiple parts with multiple physics, we might think to develop a dedicated model for the membrane, a dedicated model for the fluid, a dedicated model for any part, but then we have to, let's say, grant the continuity at the interface, which might mean, for instance, convert the variables of one simulation domain into the variables of the other simulation domain. So we will have a lot of intra-part communication issues, okay? With this generic framework, we have a natural continuity in terms of flux at interfaces. So it's also, let me say, much more elegant from a mathematical point of view. Okay. Now, before talking about the equation, we have to talk about the velocity, because the velocity vector, the fluid velocity, clearly will appear in many of these equations, I will say in all of these equations. And given the presence of porous materials, we have to introduce two different ways to talk about the fluid velocity. So basically, the fluid velocity is always the fluid velocity. We just need to specify it differently if we want when this flow develops inside porous materials. So we might talk about a superficial fluid velocity, which is also called apparent velocity or Darcy velocity. So superficial fluid velocity means that let's consider a porous material. Okay, clearly not all of the volume will be available for the fluid. Just a fraction of this will be available to the fluid, and we will call this porosity. Superficial fluid velocity means an apparent flow velocity. Okay, so clearly, if we have to grant the conservation of the mass flow rate, the velocity of each fluid particle within the reduced space available might be higher. But generally speaking, if we are not seeing inside the porous material, we are just seeing it as a black box, we will see a reduced volume average velocity. So this is the concept of superficial velocity, okay? So we would say that the fluid is slow when it moves inside a porous material. So maybe if we zoom up in the small void spaces, we will see that actually each fluid particle will have a rather high velocity because the available section is reduced. But when we look it from the outside, from far away, we will have a slow fluid velocity in a porous material. Okay, and this is the apparent velocity. The other one is the physical fluid velocity. So it's actually the proper real velocity of the fluid particle. Okay, and the relationship between these two velocities is this one here. So the superficial velocity is epsilon, which here means porosity, times the physical velocity. Porosity is, as we have introduced, the ratio of the void over the full entire volume. So the void is the volume fraction available for the fluid. So it will be a non-dimensional number in between 0 and 1. So 0 means everything is solid, 1 means everything is fluid, okay? So it's basically a volume averaging. And just to give you a reasonable number that we will use for GDL modeling, epsilon is in the range of 0.7, okay, in gas diffusion layers. So 70% of the volume is available for the fluid, roughly speaking, okay? And so this epsilon will appear in all our transport equations. When this transport equation will be applied to a fully fluid region, epsilon equals to 1. So we can consider porosity everywhere in our domain, also in completely fluid regions where we do not have a porous materials. From a mathematical point of view, this can be immediately applied by changing the porosity value to 1, which means fully fluid. So this is another very convenient and also elegant way, mathematical way, to use a unique equation, which is valid both for the fluid regions and for the porous regions. We will just change the local porosity value. Okay. Now let's start from the first equation, the continuity equation. This is a transport equation that describes the conservation of mass. Now, as we said, well, here we have the generic form of the continuity equation, where we have the presence of the epsilon term, so the porosity. Now, the first thing that we can say is that, okay, we talked about steady state form. Okay, so the first term, which is the one related to the variation in time, so in a way, the mass accumulation within a given finite volume in compressible fluids problems, this is a relevant term. Here we have no variation related to time, okay? So we will only remain with this second form here. Now, we already talked about epsilon. We have something new, especially for those of you who are familiar with this kind of equation. This SM term, this source term for the mass. I'm quite sure that in all of the CFD problems that you have studied in your career, this SM is 0. Because this means mass conservation. Here we assume a source term for the mass, which means that mass can be created or destroyed. And at a first glance, this is not a concept that can be accepted easily. I realize this. What does it mean that the fluid mass can be destroyed or created? We will understand it in a minute. So basically, this SM term will be composed by the summation of the source terms of the species, so hydrogen, oxygen. Let's talk once again about the hydrogen reaction at the anode. We have the hydrogen molecule, which will be represented by the mass fraction of the hydrogen. it interacts with the catalyst layer. So the hydrogen molecule breaks up into 2 H+ ions going into the membrane and 2 electrons going to the outer circuit. So from a fluid dynamic point of view, that hydrogen molecule doesn't exist anymore. It doesn't mean clearly that if you look at the whole physics, the mass is conserved clearly, but that has become 2 ions and 2 electrons. So if we just consider the fluid part of the physics, yes, it's being destroyed. Okay? So this is the meaning of this SM term. I mean, it's a reaction like a combustion reaction, but in combustion reaction, you have everything in gas phase. So you have the disappearance of the reactants, the creation of those products, and the mass is clearly conserved. Okay. Here it is the same, but because if we are separating the 2 half reactions and in between we have some intermediate states which are not strictly speaking fluids, because the H+ ions go as ions within the membrane. The electrons move to the outer circuit and then they recombine at the cathode. At the end of the day, if you look at the full fuel cell, clearly, yes, the mass is conserved. But the hydrogen is consumed, so at the anode, where we have just hydrogen, we will have a reduction in mass. And at the cathode, we will have a consumption in the same way of oxygen and a creation of water. Okay, so just remember this SM term is not 0 because if you look at just at the fluids, yes, mass can be destroyed or created. Okay, and this is not a physical absurdity. Okay, that's what I wanted to bring up to your attention. Now, the momentum equation. We start from the generic Navier-Stokes equation. We say that this is a vectorial equation. So here the transport, I mean, it's basically like any other transport equation, but here the transported variable is velocity itself. Okay. So, okay, we always write epsilon times u to account for the possible presence or the possible application of this equation to porous materials. Okay, here in the first equation here, if you apply, I mean, if you change the epsilon value to 1, you recover the standard Navier-Stokes equation for fluids. Okay, but okay, let's keep epsilon so that it can be applied also to porous materials. Okay. Then you neglect the time-dependent term for the steady-state assumption that we always apply, and you remain with this equation here. On the left-hand side, you have the advective term. The general meaning of these terms is always the same. And then on the right-hand side, you have the diffusive term of momentum, which is basically due to the viscous shear forces of the viscous fluid that we are analyzing. Then we have the pressure gradient. I mean, pressure gradient in nature, some consider this as part of the diffusive term of the momentum. Some other, and I prefer the second view, consider the presence of a pressure gradient, a pressure differential, as a source term for momentum, because it's the pressure gradient that generates fluid motion. So, I mean, this is more a philosophical discussion. We have the pressure gradient, which is negative, because fluids always move towards lower pressure. And then we have this term, the source term SU, which in coherence with the vectorial notation is a vector source term. Okay. Now, we have to specify this source term, especially in porous materials. When the fluid develops, moves inside porous materials, typically we have extremely low velocities, as we said at the beginning. I mean, we are laminar also in the fluid regions, but when the flow enters into the porous materials, the velocities are even more reduced. Okay. So we can assume that apart from the steady state assumption that has been already introduced, we also have the, let's say, the much reduced relevance of the advection and the diffusion term. So basically, the only surviving terms here let me just delete here, are pressure gradient and source term. Okay. Now, to specify this, again, in most of the models, the Darcy's law for porous materials is used. Okay, so the Darcy's law is, I mean, it's is one of the most famous and used relationships used I mean, whenever you have to characterize the relationship between the flow rate and the pressure drop across porous materials. Okay. It can be demonstrated from a rigorous derivation of the Navier-Stokes equation, but in its essence, it has been derived empirically. Okay, and it was first derived in the 18th century, related to hydraulic issues for the water distribution on a city, on a urban scale. Okay, so the Darcy's law relates the volumetric flow rate Q, capital Q, with K, which is the permeability, sorry, the permeability of the medium, okay, of the porous medium, and the permeability is as a unit of squared meter, divided by mu, the molecular viscosity of the fluid. Then we have A, the cross-sectional area, okay, the apparent cross-sectional area. So everything means both the cross-sectional area available for the fluid and the cross-sectional area occupied by the porous material. So when you have this porous material at your hand, just imagine like a filter fitted in a pipe. The whole cross-sectional area is A. L is the length of the duct, and we have the finite difference in pressure. Okay, and the minus sign again is to express that the flow rate in general move towards low pressure environments. Okay, in the same way as heat moves towards low temperature areas. Okay. So this is the Darcy equation expressing the volumetric flow rate. But the volumetric flow rate can also be expressed as the product between velocity and area. So epsilon ui, where I stands for the I direction, times, again, the cross-sectional area A. Okay, this is just the expression for the volumetric flow rate. And here you can easily simplify the cross-sectional area here. And from this equation, you can get for all the three directions, I, J, and K, these relationships. Epsilon times ui equals to minus K permeability divided by molecular viscosity times the pressure differential in that direction. Okay? Which, if we get back to the vectorial notation that we used at the beginning, means epsilon times velocity vector equals to minus K divided by mu times the pressure gradient, from which we can have an expression for the pressure gradient here. Okay? Now, as we said before, if we can neglect the convection and diffusion term in the steady state Navier-Stokes equation, which means that this and this are nullified, then we remain with this other expression for the pressure gradient. So here we just have that pressure gradient equals source term here. So we have two expressions for the pressure gradient, and we can equate these two expressions. So we get to this form here. So this means that our vectorial source term for the momentum can be expressed derived from the Darcy equation, okay, where we have K, capital K, which is the permeability of my porous material. So this means that when the momentum equation will be applied to porous materials, and this is what we have here, we will have epsilon lower than 1, because here we have a proper porosity or a proper presence of solid fiber that reduce the space available for the fluid. So the first modification is that we will have porosity different than unity. The second one is that the vectorial source term here is specified. So we have this equation for the flow in porous materials. But what about this equation? I mean, if we have to live with this and just this equation for the momentum in the other parts, what about the fluid parts? Well, in the fluid parts, as we already said, epsilon equals 1. So everything is fluid. And then we don't have this source term, because this source term is related to the resistance exerted by the porous material to the flow. So that's why it's a source term. It's a negative source term. Is a destruction of momentum for porous materials. Where we are out of the porous material, I mean, it will be equal to 0. And we recover the conventional steady state form of momentum conservation with no time-dependent term and with no source term. Here we will just have the momentum advection, diffusion due to viscosity, and pressure gradient. So the equation is 1. It's just 1. We can adapt it based on the local physics, on the local part of our domain. And, I mean, this is very convenient. So we don't have to introduce a separate treatment for flows in porous parts with respect to flows in fluid regions. It's the same treatment, just porosity and source term will be differently specified. And for the source term, we recalled the Darcy equation, which is very popular and used whenever you talk about the relationship between pressure drop and flow rate. Okay. Now, moving to the other equation, but as we said, all of these are transport equations, so it's not really another equation. We are moving to another variable that is transported with the same model. Chemical species. Chemical species is whatever physical species you have in your domain regarding fluids. So we will, and the same equation will be applied to all of this. So with the PEDIX K, we can write the generic transport equation for the mass fraction, which is YK, of that species. So again, we have the unsteady term, okay, so the variation of mass fraction in time for that specific finite volume. We have the transport due to flow motion of the mass fraction of that species. We have the diffusion. You see the diffusivity coefficient, capital D, and then we have the source term. So again, the model is the same. Just as a note, typically we talk about mass fraction Y, and this is also because most of the CFD codes use this variable to represent the presence of a species. But in the same way, you might talk about mole fraction instead of mass fraction. And the mole fraction are generally written as XK, okay? Based on the code that you use, you might have different formalism, but the general meaning is absolutely the same, okay? Now, again, we can neglect the time-dependent term, and we remain with a conventional advection and diffusion plus source term equation for the transport of this mass fraction. Okay. Now here, how many species do we have in our fuel cell? For sure, we have hydrogen, 1, oxygen, 2, water. There might be water. I mean, water is a product, so it makes 3. And if we use the oxygen from the atmospheric air, we will also have the nitrogen, 4. Okay, so we have 4 species, but we have this condition that helps clearly the mass fraction of all of your species must sum up to the perfect unity. And this is valid also if you were considering mole fractions or concentrations. So the summation must be the unity. So this is why even if we have 4 species, we can solve just 3 transport equations, because the last one can be obtained by difference from the unity. I mean, the mass fraction of the 4th species, nitrogen, if you want. Nitrogen does not have an active role in our electrochemical reactions, so we can leave nitrogen aside, and the solver will just recalculate the local nitrogen concentration by complement to unity. This is why we have the summation up to k minus 1. Okay, we can solve one less transport equation than the actual number of species. Okay. Now, again, the generic model is very simple, and it resumes all the possible transport mechanisms and generation mechanism of our generic species K. Now, the complexity, if you want, comes from how can we specify this equation model to the specific problem that we have. And here the specification will be related to the effective diffusivity term, this dk with the apex f, which means effective, and in the source term. Okay? And this is what we are going to talk about now. Now, the diffusion coefficient. The diffusion coefficient, or the diffusivity coefficient, is just a property of that species, of that fluid, that describes the rate of diffusion that is at the basis of the, again, of the diffusion process. So imagine that you have a concentration of that species K, you have a source, a local source of that species K, like a local injector of that species, how fast it will diffuse in the surrounding fluid environment if there is no mean flow. So just because of gradient differential, gradient concentration, this is the diffusion. Okay, and different species will diffuse at different rates. So it's a property of that species. And typically, these diffusivity coefficients, which are here represented as dk0, 0 means at reference conditions. Okay, you can find it quite easily in databases, in your CFD software, or in generic tables. And these are the most common values that you might find here for water, for oxygen, and for hydrogen. So sorry, hydrogen, oxygen, and water. Okay. I just underline here that for the okay, for hydrogen here, yes, this coefficient is already 1 order of magnitude higher than the other species. So this is one peculiarity of hydrogen. Hydrogen diffuses at an extremely higher rate than the other species. This is also why when we talk about the deficiency of a reactant, the transport of a reactant, hydrogen is never really an issue. Hydrogen diffuses, so it means a spontaneous transport much, much faster than the other species. Okay. But anyway, this coefficient here is known. You know it quite easily. The first operation is that temperature and pressure alter the diffusion process. So temperature, as we said in the last lesson, helps diffusion. So if we operate at a higher temperature, we generally expect faster diffusion. And this is usually represented by this term, T over the reference temperature elevated to the power of 1.5. So it means that temperature helps increase the diffusion. The other way around, pressure obstructs the diffusion. So a higher pressure means a denser environment. Okay. So we have P0, reference pressure, divided by P. Okay. So this is for the variation of temperature and pressure. But then, again, we might have the diffusion of this species inside a porous material if we have to use the same equation. And for porous materials, the most common correction or modification of this coefficient is the so-called Brueggemann correction, which means that this dk coefficient is multiplied by epsilon to the power of 1.5. Epsilon is lower than 1, so it means that here we are actually reducing the diffusivity coefficient. And this makes sense. I mean, if that species will have to diffuse in a perfectly fluid environment, it will have its own rate. But if that diffusion has to develop inside a porous material, it will be obstructed. So the rate of diffusion inside a porous material is lower. And this is accounted for by this Brueggemann correction. Okay? But then again, we might have another phenomena, especially for catalyst layers, where the void spaces, the pore of the porous material, become so small that it is comparable as an order of magnitude to the mean free path of the molecules. So we already talked now about the diffusion inside a porous material, okay, where we account for the obstructed diffusion with the Brueggemann correction. But once we consider a porous material whose pore, so whose void space, becomes comparable in size, in length scale, to the mean free path of the molecule, so extremely small pores, we have another diffusion coefficient to consider, which is the so-called Knudsen diffusion, which is this coefficient here that you see is related to the mean radius of the pores. So this is another contribution to represent the diffusion inside a porous material whose pores are extremely low. And this is typically this Knudsen diffusion is most of the times neglected because is considered to be absolutely negligible. You might find it included in porous materials, because in porous materials it's not negligible anymore, let's say. And all of this is accounted for in this effective diffusion coefficient. So this decay effective that we had in the general transport equation, now you know what is composed by. It's composed by the molecular diffusion, which is modified based on pressure and temperature, which includes, if needed, the effect of porous materials with the Brueggemann correction, and the Knudsen diffusion if relevant. Okay, so it's by all means an effective diffusivity. Okay.
Whether this Knudsen diffusion is used for ion transport because it travels through the porous structure.
One of your colleagues asked if this is used for the ions transport. Actually, no, because in this model, the ions transport will be just related to the membrane. The membrane will have a separate treatment. The membrane is maybe the only component where we will apply separate treatments, and we will talk about diffusivity and mobility of the ions in the membrane. So no, this is just related to the fluid species.
Okay, thank you.
Yeah. So we talk about the diffusion coefficient. We also have to talk about the source term, this Sk that appears in the last term. In most of the parts of the regions of our fuel cell, that Sk term is 0. Okay, so, and I mean by this, everywhere apart from catalyst layers. If we are in the gas channels, if we are in the gas diffusion layers, these species are just transported by convection and diffusion. So this is the transport equation, the steady state form of the transport equation with no source terms. Because the source terms are related to electrochemical reaction, and electrochemical reaction are just at the catalyst layers. So if we are away from the catalyst layers, I would say everything is quite easy, okay? It's just a matter of an effective diffusivity. If we are at the catalyst layers sites, then there is the source term, because here species are created and are destroyed. And this Sk term, based on the specific species that we are considering, so if it's hydrogen, oxygen, or water, is expressed by these expressions here, which are derived from the Faraday equation. The Faraday equation basically relates the electric current with the flow rate of species, okay? So here we have for the hydrogen and for the oxygen a negative sign, which means a negative source. These are consumed by electrochemical reaction. On the contrary, water is produced, so water is positive. Okay. We have this at the denominator, 2 times F. F again is the Faraday constant. Okay. 2 for the hydrogen and water, and 4 for the oxygen, because for each mole we have respectively 2 and 4 electrons that are involved in the process. Capital M is the molecular weight. So this is, by all means, the Faraday equation, which is manipulated to become a source term for each given species. And this expresses the developing of electrochemical reactions. So this source term here, from a general point of view, is extremely important, because this is the point of the whole modeling framework, where we couple the electrochemical domain with the fluid domain, because here fluid is consumed based on local electrochemistry, local J. J here is the volumetric current density, so ampere per cubic meter. So here, in the source terms of the fluid, we have the presence of the current density that is produced. Here is a current per unit volume, okay? But here, this very simple source term actually is extremely important, because it is here that fluid flow, so fluid domains and electrochemistry are coupled one to each other. Each species is consumed proportionally to the local current, and the local current is produced based on the local reactant consumption. Okay. And an additional note for water: these expressions here are just related to electrochemistry. For water, there is also another aspect to be considered in the general equation, which is the electroosmotic drag. We will talk about this. Generally speaking, this relates to the hydration state of the membrane. The membrane absorbs some water, okay, and at the anode side, and it will release this water at the cathode side. So we might include in the general equation a negative term for water at the anode and a positive term for water at the cathode, which will be summed to this term, but which will be different in nature. This is the water produced, created by electrochemical reactions. Everything related to the membrane adsorption or desorption of water, it still refers to water, but is not related to electrochemical reactions, okay? So just bear in mind that the water source term will have also an additional contribution, okay? But if we just talk about the electrochemical reactions, these are the source term. And again, this is where fluid domain and electrochemistry domain are coupled, okay? And just to conclude this, it will be the summation of this K species that will create the source term of mass that we have seen in the first equation. Okay. So now I hope that it is clearer. Why do we see like an apparent destruction or creation of mass? It comes from the electrochemical reaction of each species, which will sum up as a source term for mass. Okay. Now, this J, the volumetric current density, how can we represent it? For those of you who are familiar with electrochemistry, here we use the well-known and popular Butler-Volmer equation, okay? Which here you see applied at the anode and at the cathode. This is for anode and this is for cathode, okay? It's composed by several terms, and it can be derived by the equilibrium between the forward and backward reaction that you might have at any electrode, and this is the final form of these equations. Basically, you have the difference between two exponential terms here, where we have eta, which is the activation over potential, okay? So again, this is the loss of voltage related to the onset of electrochemical reactions. You have these alpha coefficients. These alpha are called the transfer coefficients, and there is a lot of uncertainty and discussion about these coefficients from an electrochemical point of view. You might use 0.5 is the most common value that you will find, but just bear in mind this is not the unique one. Okay, R is the universal gas constant, T is the absolute temperature, F is the Faraday constant, and this difference in these two exponential terms here is pre-multiplied by the exchange current density. Okay, which is the term that you see here, but which can be further decomposed into the contribution of different terms. This exchange current density can be calculated starting from a reference exchange current density that typically comes from an empirical characterization of your electrode. Okay, then you might have a coefficient, which is also called electrochemical surface area per unit volume. So how much surface, how many squared meter or squared centimeters do you have as a rough surface available per unit volume of your catalyst, of your electrode. Then you have the ratio of two concentrations, and you see here the effect of pressure that we talked about in the past lessons. If you increase the pressure, you increase the partial pressure of your species. So the concentration, the presence of that species at the electrochemically active sites. So all of this term, and this can be decomposed even more, okay? But this is the generic and most common formulation that you find for the Butler-Volmer equation, including the presence of the exchange current density. So again, we say the exchange current density should be, or we want it to be as high as possible, because it increases the volumetric current density that we see here represented by these equations. And just to give you an idea, when we talk about anode and cathode, maybe we have the same platinum deposited with the same concentration, the same loading, both on the anode and on the cathode. So when we realize, when we produce the cell, it is perfectly symmetrical around the plane of the membrane. Okay, but exchange current densities are not just related to how much platinum or the nature of the catalyst that we deposit. It's also related to the species with which this catalyst will react. So the same amount of the same catalyst, platinum, will be represented by these empirical exchange current densities with orders of magnitude of difference between anode and cathode. And typically, you might have values like, just to give you an order of magnitude, this reference here, this I0 reference at anode might be in the order of 10,000 ampere per square meter. The same amount of platinum at the cathode, just because it reacts with oxygen, less diffusive and less active than hydrogen, we might have a reference exchange current density at cathode of 0.001. Okay, so this is where the extremely different orders of magnitude, many orders of magnitude of difference between anode and cathode is introduced in the equations. And that's because it's not just about the catalyst, it's also about which species reacts with the catalyst. And this is also what explains why the cathode is always the slower side of the cell. The limiting factor in all the fuel cells that you will, of this type that you will encounter, as I was saying, the limiting side will always be the cathode. And you see this from the electrochemical point of view. I mean, once you introduce this to compose this term, you understand why. Okay? So all of your effort, all of your engineering effort will be to improve the cell operation at the cathode. Okay? Now, let's move to the energy equation. And again, like the other equation, we can write a generic form for the transport, for the conservation of energy. Okay, energy is extremely important. Energy and the local temperature that derives from the distribution of energy among the parts is extremely important for low temperature fuel cells, because we said how much relevance the membrane hydration has. And the membrane hydration is tightly coupled with the temperature. The cell temperature must stay around 80 Celsius degrees. If it goes higher than that, then the membrane will become more and more dehydrated. Okay. But generally speaking, also in high temperature fuel cell types like high temperature PEM or solid oxide fuel cells, we will have a relevant heat generation by several mechanisms that we will see now. But just think about the second principle losses. So the losses related, expressed by the product of temperature time entropy change. That happens where electrochemical reaction happen, so at the catalyst layers. So all of that heat dissipation that we talk about when we talk about the Gibbs free energy versus enthalpy, so the difference is the second principle losses. Okay, that's valid in general, but where is that happening? It's happening at the catalyst layers. So that large amount of heat is dissipated in extremely small and thin components. So the local generation of heat will be extremely high. Okay, so the distribution of heat on the parts composing a fuel cell is very important for the local distribution of heat. Now, we can write the general conservation equation for the energy here, and again we can neglect immediately the unsteady term. Okay, here you see the partial derivative on time. And what we have here, I mean, it seems more complex than we expected, but it's just, again, to account for the possible presence of porous materials. So we will have, I mean, we are talking about the product between the density and the specific heat, what is usually called the heat capacitance of a given material. In porous materials, we will have both a fluid and a solid. So what is the effective heat capacitance? I mean, we can use the porosity as a volume weighting operator. The porosity is de facto the volume fraction of fluid. So the effective heat capacitance will be the porosity times the heat capacitance of the fluid material plus the complement to unity, so the solid volume fraction times the heat capacitance of the solid material. Okay, this is what we can call an effective, again, heat capacitance. Okay, and the same can be carried out for the lowercase k is the thermal conductivity. What is the thermal conductivity of a given finite volume of porous materials? It will be partly composed by the thermal conductivity of the fluid and partly by the thermal conductivity of the solid fibers. Okay, so it's always the same approach. And this is because we are using a macrohomogeneous approach. Okay, so we only need to know how much volume is for the fluid and how much volume is for the solid. Okay, so again, very, very, very convenient. And then we have this source term ST. Okay, so this is the generic transport equation. Now, I mean, for this effective source term, there might be specific correlations. Just to mention it to you, it's not reported here. Typically in porous materials, the effective thermal conductivity is represented by the Dagan correlation. We will see it when we will talk about gas diffusion layers. All of these are basically linear combinations of the presence of fluid and presence of solid. Okay. Here, I'd like to spend a few minutes on the source term. So what generates heat? We might have several mechanisms, and we have to account for all of them with our equation. And also several mechanisms for the heat transfer. So it will not just be the heat generation, but also the heat dissipation, the transfer towards the outside of the cell, towards the cooling circuit. Well, in fluid regions, in gas channels, here, basically we have just fluids moving. So the heat will be transported basically by convective mechanism. Okay. So we'll have a convective transfer in the fluid regions. In the solid regions, so membrane and bipolar plate, it will be a conduction heat transfer. And in porous materials, we will have both. Convective within the void spaces where the fluid develops, where the flow develops, and conductive through the solid fibers. Okay? Just, I mean, I anticipated to you since the beginning, in porous materials where we have both these mechanisms, clearly the conduction through the solid fibers is by far the most effective mechanism for heat transport. So in gas diffusion layers, the role of heat transport is much more on behalf of the solid fibers rather than the fluids, okay? But generally speaking, we have to account for both of them. Now, first contribution to the source term of energy, activation over potential. So the activation over potential generates some heat, okay? And again, this only happens at catalyst layer. So a first cause for heat generation at the catalyst layer is the overcoming of the overpotential related to the activation. So this is a first motivation for heat generation. Then we have the heat generation due to electrochemical reactions. And again, this is at the catalyst layer only. So second contribution is related to the product time, the temperature times delta S divided by 2F. Again, this is multiplied proportional as it was for the activation term to the local volumetric current. So the more current we produce and the more heat we generate, okay? And again, these two, contribution 1 and contribution 2, are only at the catalyst layers. So we have a lot of heat developing there. And this becomes even more critical if we want to operate our cell to produce a lot of current, okay? Another contribution, sorry, this is a 3, is due to the ohmic losses. Ohmic losses means that we already introduced the ohmic losses is the resistance to the flow of current of a charged species through conductive parts, okay? Now, a current of a charged species through a conductive part also generates some heat associated to that, which is the well-known Joule effect, okay? And we can introduce this as an additional source term, which can be represented here. So the current density squared, so this becomes, is much more than linear. We have a power of 2 related to the current density. So it means that if we want to operate at a high current density, not only we increase, let's say linearly, the activation and electrochemical source terms of our energy, but we increase with a squared power the heat generation due to Joule effect. Divided by, this is Greek K and this is sigma. These are the effective conductivities. Greek K is for the electronic conductivity and sigma is for the ionic conductivity. So generally speaking, the conductivity from an electrical point of view of our component, okay? It means that the lower is the conductivity, so the worse is our material for charge conduction, and the higher will be the heat generation due to the flow of that current. So this is also why we need to select good conductors, because good conductors means a very high conductivity, and this source term will be lower. Okay, good conductors generate a low amount of heat because of Joule effect. In catalyst layers, actually, we have both. In catalyst layer is where we have both the ion current and the electric current. At the anode, these two currents are generated, and then they will divide in their paths. At the cathode catalyst layers, these two currents combine with oxygen to generate water. Okay, so at the cathode, actually, we have both these currents. So both these Joule effects, the one associated with ionic current and the one associated with electronic current. Okay. To sum up, this source term for temperature can be composed by these three terms: activation, electrochemical reaction, and Joule effect. Now, at catalyst layers, we have the full expression, because at catalyst layers we have all these sub-processes contributing to heat generation, active, developing, generating heat. Okay? So catalyst layers are the most critical parts for heat generation, because we have also the heat generation terms associated to the electrochemical reactions, which happen only at catalyst layers. What about the other parts? I mean, in the porous materials, in the bipolar plate, basically we have just the ohmic contribution. Yes, there is some heat that is generated because we have the flow of a current, but the situation will be clearly much easier for the other components. So basically, in all the solid components of a fuel cell, we have some heat generation, because in all the solid components, we will have some current flowing. In the membrane, we will have the ionic current. In the solid phase of the gas diffusion layer and in the bipolar plate, we will have the electronic current. So wherever we have some charged species flowing, wherever we have some current, we will have some heat generated due to Joule effect. But generally speaking, both because it's the only contributing factor, and because if we select good materials for the conduction, this heat generation is much reduced. The most critical situation is at the catalyst layers, where we have also activation and electrochemical reactions. Okay? But again, if you represent this source term, including all the possible reasons for heat generation, then just based on the local part where this equation is applied, on the local finite volume, you can suppress or not a specific term. So again, this gives us a great flexibility of the unified set of equations. With a single equation, we account for all the possible parts and all the possible generations, in this case of heat. And then, based on the specific part where we are, the source term or the diffusive term are specified differently. Okay? Now, let me conclude with the last equation, the transport of charge. Again, we have always to consider two typical two currents. One is ionic current, which is related to the ionic potential field, which means through the membrane, and the electronic current that will flow based on the gradient of an electronic potential field. Okay. So we have two charged species, two currents. We need two transport equations, which are this one and this one. You see that they are identical in nature, but they will refer, the first one with the pedix S, to the solid, let's say, electronic parts, and the effective electronic conductivity is capital K, Greek K, sorry. The other one is for the ionic current, and the ionic conductivity is sigma, okay? Now, charge flow, charge motion only develops in solid parts, okay? The fluids can be considered with a good approximation as insulators, okay? Clearly, all of the fluid species will have an electric conductivity, but it is extremely lower and reduced compared to the conductivity of the solid part. So that is why we can consider the transport of charged species only developing through the solid materials. Okay, and at the catalyst layers, we will have this relationship between the two current densities. One is the electronic current density, the other one is the ionic current density. Okay, that's it. And based on this, we will obtain the local electric current and ionic current. Okay, again, the minus sign means that we are moving. I mean that the current is moving towards negative gradients of potential, both electronic and ionic. I mean, the dynamic of this charge transport is identical, okay? It's just based on a different potential. We will have different conductivity properties of the materials, but it's absolutely identical, okay? Now, this concludes the generic framework of equations, okay? So you see that if you consider the number of transport equations, they are relatively reduced, considering that we will apply this to fluid, solid, and porous parts, okay? For each variable, we use just a single equation. Then we adapt it in diffusion terms, source terms, and so on to the specific part. So the complexity is more in the specification of that equation, but the number of equations is reduced to a minimum. And this is why it's been developed as the most common framework of equations, okay? Now, up to now, we didn't talk about the multiphase issue because clearly our model needs to be at least a bit made more complex to account for the possible presence of more than one phase. Now, in the context of fuel cells, here I'm just focusing on the most common treatments for multiphase in fuel cells. As we said at the beginning, the treatment of multiphase flows goes way beyond this course and also more extended courses. It can be an extremely different range of scales of fluids that are of interest in multiphase simulations. Okay. Generally speaking, those of you, for instance, who are familiar, as I am, with internal combustion engines, are really familiar with multiphase flows in the sense of high pressure sprays of fuel, for instance. And in that context, typically, several models were developed in the context of Lagrangian multiphase. Lagrangian multiphase models identify a class of models that are devoted to representing, even from a statistical point of view, the presence of the individual droplets or of classes of droplets that are immersed and move inside a continuous so-called Eulerian phase, which is the gas phase. So we have a transported, dispersed phase within a continuous phase. And this describes the Lagrangian multiphase models. In the context of fuel cells, another type of Lagrangian models is very used, which is the so-called Eulerian multiphase models. Now, Eulerian multiphase means that we don't want to track or identify the boundary between the two phases, so the interfacial surface. Okay, we can live with a fully Eulerian framework, So we have no dispersed phase to track or to transport. But we are happy with a volume fraction of fluid, liquid, versus a volume fraction of fluid, vapor. So we are happy just with volume fractions, okay? And in the context of Eulerian multiphases, two models gained a lot of popularity and demonstrated their application in fuel cells. Again, none of these models was developed for fuel cells, but the application in fuel cells, the application to fuel cells, really benefited of these models that became, in a way, like the standard for multiphase modeling in fuel cells. Now, the first one is the so-called mixture multiphase. Imagine that we are at the cathode of a fuel cell and you are generating some water which is in a liquid phase. Okay, so imagine that you have a multi-phase flow where most of your flow is in gaseous phase, and then you have some droplets of liquid which are finally dispersed in your gaseous phase, like a mist of very small liquids droplets. The two phases are by nature immiscible. I mean, that's why they are separated. One, a part of the volume is in gaseous phase, the other part is in liquid phase. But if you're not interested into tracking the individual droplets, you are just interested into knowing how much liquid do I have. Then you can consider a unique mixture fluid. Okay, mixture fluid means you basically create a mixture, so you make miscible two immiscible phases. Okay, so you are happy with considering a unique mixture. Okay, so you don't have a univoc specification of your mixture. Then you have to specify how much of your mixture is liquid and how much of your mixture is gas. But you can write all of those transport equations that we have seen, not for the fluid, but for the mixture. And that's why usually you find a pedix m. So the velocity is not anymore the velocity of the fluid, it's the velocity of the mixture of vapor and finally dispersed droplets. Okay. Now, clearly, this is an approximation that at first can be acceptable if the volume fraction of your dispersed phase is much reduced, so where you have a clearly dominant phase over the other one. Okay, and again, this is usually carried out based on the volume fraction, but consider that if you talk about water in vapor and in liquid phase, even if the volume fraction of the liquid phase is very reduced, so yes, you have these finally dispersed liquids, the density of those liquids is approximately 1,000 times more than the vapor phase. So even if when we talk about volume fraction, these are negligible, so they occupy a very small volume, the mass contained in that very small volume might be absolutely relevant because the density of the liquid is much higher. So this class of model is really valid in theory only when there is a clearly and evidently dominant phase over the other one. In this case, gaseous over liquid. Okay. But this simplifies your life because you transport just a mixture. So you solve one transport equation for the momentum of the mixture, and then based on algebraic formulation, you reconstruct how much liquid and how much gas you have in that finite volume. And clearly, you also have to consider that gas and liquid might have different velocities. Even if you consider a single mixture velocity, that mixture velocity might be composed by the interaction of a gas and a liquid. So you might have drag and resistance forces to compose the global mixture velocity because your liquid and your gas might have different velocities. Okay, so again, this is implemented in a way in the complexity of reconstructing the different velocities of gas and liquid. But from a general equation point of view, this simplifies your life because you just have a mixture to transport. Okay. The second very popular, I would say this second model is more popular than the first one, is the, let's say, it's called Eulerian multiphase. It's a little bit improper because also the first model that we talk about is Eulerian in nature. So you don't have Lagrangian dispersed phases. Both of these are Eulerian. So if you want, we can more appropriately call this, this is also called, this is also called two fluid model. Okay. Two fluid model. And this is because this is the most exact representation that you can carry out with a Eulerian model of two phases. You solve two sets of transport equations, one for the gas and one for the liquid. Okay? Both of these are Eulerian, so you don't, you are not able to see where is the boundary between the two phases, but you don't care. Okay? You transport the liquid. Clearly, these two sets of equations will have to be coupled using a volume fraction concept. But you have a dedicated transport for the liquid water, and you have a dedicated transport for the gaseous water. Each of these will have their own specific terms, and thus these two equations will be coupled. Numerically speaking, is a little bit more complex, and clearly you might have much more frequently stability issues with this kind of models. This might depend also on the code that you are using. You will find these two approaches, I would say, in all the CFD codes that you might use in your career. Okay. As I was saying, this is, let's say, the most exact multiphase, Eulerian multiphase model, because you have dedicated equations for each phase, and you don't introduce the assumption of a unified mixture of different phases, which, I mean, might be something to be discussed. Okay. Finally, volume of fluid. Again, these volume of fluid models are extremely used in engineering simulations. And I mean, in these models, these are not properly Eulerian, because here you are really trying to reconstruct the surface that separates the two phases. Okay. So in this volume of fluid models, these are very popular in like in sloshing or mixing problems, or in oil jets or water jets. They make, especially in the recent years, a large use of mesh refinement techniques, something like adaptive mesh refinement, because clearly, if you want to reconstruct, these are also used in navigation issues. If you want to simulate a boat using a CFD, imagine that you have to numerically reconstruct the surface between the water and the air. You would want a high mesh resolution around the interfacial surface. Okay, so with the development also of adaptive mesh refinement algorithms, and these today are more or less present in all CFD codes, the volume of fluid method will have a much wider popularity in the future years than what has been received until now. You might find isolated application of VOF in fuel cells. Clearly, I mean, if the focus, let me say that if the focus is to show with a CFD simulation where the liquid droplet forms, I will say that this is more for creating a nice image rather than providing a really useful information. So yes, it's nice to see where the droplet forms, but I would say it's much more useful to know how much, to what extent that electrode is subjected to flooding, for instance. Okay. And but I mean, just bear in mind that you might find in these years, in these upcoming years, a much more intensive use of VOF model for all multiphase problems, but especially for fuel cells. Okay. And so, generally speaking, if we let's say if we use the first Eulerian model that we have used, the mixture multiphase, In our experience as a research group, we used this first Eulerian model for all our applications. Okay, so basically you talk about a mixture fluid velocity. So you have this pedix m, and this relates also to other properties like the density. You don't have a fluid, so it's not anymore the density of the fluid, it's the density of the mixture. Okay. But if we have to resume everything that we have said today, we have continuity equation where this SM term based on the region, GC stands for, let's say, gas channels. So this means fluid only, okay? Fluid only, gas diffusion layers, catalyst layers. So these two are different porous materials. So they will receive more or less, apart from electrochemistry, the same treatment. They might have different properties, different porosities, permeabilities, okay? And then the solid parts. So the same equation can be differently applied and adapted to all the solid parts. And the same is for the momentum, okay? Again, this is what we have said. For fluids, we have porosity equal to 1 and no source term. For porous, we will have the Darcy term for the GDL, where you see that there is here the permeability of the GDL, which might be different to the permeability of the catalyst layers, but the treatment is the same. Okay, we have a momentum resistance expressed by a Darcy type equation for both the gas diffusion layers and the catalyst layers. Okay, and then we have, in solid parts, both for the continuity, we have no velocity at all, clearly, and this is also for momentum. For the species, okay, you see that the source term in fluid and porous materials is 0 because there is no electrochemical reactions here. In solid parts, we have no fraction, no mass fraction of the fluids. And in the catalyst layers, something happens. Here we have the electrochemical reactions, okay? And I just want to highlight here what we said before. We have terms related to electrochemical reaction. Let me highlight them. For the water at the cathode, we have this term. This is the water creation at the cathode as a product of electrochemical reactions. Then we have hydrogen consumption at the anode. Hydrogen is a reactant, so it's consumed. Oxygen at the cathode is another reactant, so it's consumed. So all of these yellow contributions are the electrochemical reaction source terms deriving from the Faraday equation that we have commented before. But for water, we have a term at the anode. This is not related to electrochemistry. This is the adsorption in the membrane. And the same term with the opposite sign will be as an additional source term at the cathode. Again, this is due to the electrochemical, so it's also called electroosmotic drag. So it's an electrochemically related drag transport of water inside the membrane. So it's like water is consumed at the anode and produced at the cathode because it's adsorbed and desorbed following the H+ ions in the membrane. So it's included in the source term. We will talk about this, but it's not related to electrochemical reactions. Okay. Finally, for the energy, we have said, we've talked about these source terms. I mean, basically, in fluid regions, we have no heat generation. In the GDL, we have only the Joule effect, as we have in the other solid parts. Okay. In the catalyst layers, we have everything. Okay, so here catalyst layers are the critical ones for heat generation. Most of the heat is generated at the catalyst layer. So in these two layers mounted right on the two sides of the membrane, and the membrane needs to stay hydrated. That's why it's critical, the heat dissipation, because we are generating heat right adjacent to the membrane. So where the dissolved water must survive inside the membrane. So we really need to be good in dissipating this heat outside of the cell. And finally, we have the two coupled similar transport equation for the charge. One for the charge of electrons, the other one for the charge of ions. Okay. So this concludes the framework of the transport equation. So in a way, this was to give you an overview of the transport equations to use CFD in fuel cell systems. And again, we can be back now at the end of the lesson understanding what did we mean at the beginning by coupling the fluid with the solid with the electrochemical, and the electrochemical with the fluid. We mean all of these sub-processes. The heat dissipation couples the fluid with the solid. Electrochemical reactions consume the fluids, but also generate the charges that will migrate through the solid parts. So this is what makes the CFD simulation of fuel cells so peculiar, so special in a way. Okay, despite again the apparent, the simplicity of the components, actually the physics that develops within these components is absolutely interesting and coupled, and there is not a single part or a single component of a fuel cell, bipolar plate, gas diffusion layer, membrane, whatever, there is not a single part that is doing just one job. So you can never say to improve one aspect, okay, let's modify this component in that way. You will always worsen some other transports. So that is also why the numerical modeling of this is very useful and helpful. It will always be about trade-off between different and competing mechanisms. So it's not trivial to predict it at a first glance. You might use simulations to find the optimal trade-off based on quantitative results. Okay. And I mean, these are just a few modeling examples that we ran in our research group. This is for a conventional triple serpentine hydrogen air fuel cell. You might see on the catalyst surface what is the mole fraction of hydrogen and oxygen. And again, you just imagine to measure this in a lab on a working fuel cell. It will be very hard. Clearly, you see from the inlet, it's not reported in this picture, but here clearly, this is the inlet and this is the outlet. And the general path, apologies, you can't really see it probably. This is the path of the fluid, okay? It is consumed moving from the inlet to the outlet, and the oxygen does the same, undergoes the same process, consumption. Water is formed, and temperature increases from the inlet to the outlet. Okay, so all of these spatial representations, apart from the nice figures that you can generate, really give you an inside view of what's happening inside a fuel cell. Whatever is your focus, it's electrochemistry, it's thermal distribution, it's consumption of reactants, is the hydration state, everything is coupled, okay? And I think the very nice thing is that you can get an explanation of what happens and why. And this gives you, I think this is the only good starting point to generate new ideas on innovative designs, on improvements of a given design, okay? And those pictures were related to the membrane, to the catalyst, I mean, on the membrane. And here is the cell temperature on the outside. I mean, clearly in this first picture, you see an extreme heat generation. I mean, here we are way above 100 Celsius degrees. So actually this fuel cell operates very badly because in all of this hot part towards the outlet, we expect to have a fully dehydrated membrane. I mean, the water can't stay in the membrane, okay? And finally, we have the electric current density. So basically, just imagine that your polarization curve, like the one that you are used to see here as I, and your polarization curve like this one here, actually each of these points, so maybe you are reading this for a given voltage and current, this is like the surface integral of the current density that you see here, okay? Once you only read the polarization curve, you don't know anything about the spatial distribution and the local inefficiencies that you might have. Once you have this kind of models, not only you see the global value, but you also understand if your cell is operating in the uniform and optimal way that you designed it for. Okay, so I think this is really the added value of this kind of simulation. You might identify, like in this operation here, local areas of overheating that lead to dehydration, that lead to poor ionic conductivity, so poor electrical generation. So all of these kind of considerations are really the battleground for CFD, and this is, I think this is the ultimate goal for the developing and knowing of these kind of models, okay? Okay, and as always, this is a very concise bibliography of the, I think, the most excellent sources on this topic that we talked about today. So the generic framework of equations. The first two, as I said at the beginning, are two generic sources for CFD. I mean, any kind of CFD. And then the other sources are more related to the application and adaptation of these equations to the context of fuel cells. Okay. Now this concludes this lesson. I mean, today we really got into the CFD world. So we started handling transport equations. Okay. But I mean, I hope this was clear enough for you to understand how this can be adapted and what is the relevance of their adaptation to the context of CFD. Yes, we can study them using CFD. If we want to run a good CFD, we need to know some specific aspects that require a special care. Okay. Now I think I can stop here my screen sharing. And this concludes today's class. So thank you all for attending.
I have one question.
Yeah, sure.
In reality, if you have a stack, how good do you simulate? You take a periodic conditions, or because that is logically not so correct to just consider a periodic condition for a complete stack. You have a flow difference, flow pressure changes from inlet to outlet. So how it is taken in reality in industry?
Yeah. The question of your colleague was how can we adapt this to the simulation of a full stack, which is clearly a very good point. I mean, until now we always talk about the single cell. Well, in principle, you can, I mean, the most obvious choice will be, okay, why don't you create a 3D model of your stack? The first answer is that the computational effort is probably way too expensive. I mean, it's not just because of computational resources, but you might very easily go in the range of tens or hundreds of millions of cells. So yes, you can in principle apply this same set of equations to any number of individual cells. So this equation in principle will be good to describe the behavior and the different operation, different hydration states of each cell in the stack. But from a practical point of view, this is not affordable most of the times. So how can you replicate this? I mean, typically the most common choice, which makes sense, is that you can use a, let's say, 0 or 1-dimensional model of your stack. I mean, you mentioned the pressure losses, so degree of reactance feeding of each cell. you might use a lower order model of your entire stack to derive the pressure losses and use this as a generator of boundary conditions for your individual cells. And then with 3D CFD, like with the models that we talked about in this course, you might simulate the representative state of a first, intermediate, and last unit cell in your stack. So this is the I think this is the most logical and the most common in literature way to adopt these 3D models to a full stack. Another way is to replicate in 3 dimensions the entire stack, but clearly maybe you don't simulate the detail of each and every gas channel. Okay, so you introduce some simplifications that are needed for the overall computational cost at a channel level. Okay, so maybe you reduce the number of computational cells in your gas diffusion layers, in your catalyst layers. If this doesn't create you numerical instability, because whenever you reduce the number of centroids, basically of finite volumes, your solver might be absolutely not happy. Yes, you are reducing the number of cells, but the solution of those equations on a lower and to the limit to one centroid might create a lot of numerical instabilities in terms of fluxes at the interfaces. So if you do not have stability issues, you might introduce some simplifications in the resolution, in the local resolution of the flow at your gas channel. So in this way, you might contain the total number of cells, so your total computational effort for a full stack. This is a very important point. I mean, nowadays, the interest for an upscale of the fuel cells engineering is at the stack level. So I personally think that this kind of models will be extremely useful to describe what happens at a single cell, but we will necessarily need other type of models to have a broader view, a large picture view of our stack. And then I think that the most virtuous approach will be to integrate these 0 one-dimensional models with 3-dimensional models. So in this way, we have both the detail and the comprehensive view of the fuel cell. But yeah, I mean, that's my opinion, and also based on the computational resources that one might have at hand. I mean, you can find in literature examples of stacks fully reproduced in 3D. Probably you will find in reading the paper some assumptions that are done to simplify the geometry and the number of grid points. But yes, it is possible.
Okay, thank you.
Yeah. Okay, in the next lesson on Wednesday and the next week, then we will talk with more detail about gas diffusion layers, catalyst layers, and bipolar plates. So we will go into the detailed, I mean, today we talk about the general framework of equations, then talking with more detail about gas diffusion layers, what are the typical values of gas diffusion layers? If you have to run a simulation of a fuel cell, what do I use for gas diffusion layers? Do I have to read every paper that is published in literature, or can we start with some more typical values? And so the same will be done for catalyst layers, membrane, and bipolar plates before giving you a final overview of fuel cells in the automotive industry today. Okay? Well, thank you very much for attending, and see you on Wednesday. Goodbye.
Thank you.
Thank you. Goodbye.
Thank you.
Thank you.
Goodbye.
Thank you.
Thank you.
Thank you.
Yeah. Mm-hmm.